Thermal conduction is a phenomena of transmission of the heat where no particle of the medium has permanent displacement. No particle has permanent displacement. Each particle vibrates about its main position, transmits the heat energy to the next particle. That's possible when the molecules are tightly packed. That happens in a solid material. So, thermal conduction happens in solid materials. So, you supply the heat, each particle pick up the energy, vibrate about its main position, transmits the energy and comes back. Like that, finally it will go from one end to other end. So this kind of a phenomena where no particle has got a permanent displacement and vibrations happens about main position is called thermal conduction. So let us imagine a thermal conductor, a solid material like iron. The heat has to go from this place to this place. That the heat that has to go is from this end to that end. How much heat flows, the magnitude of the flow of the heat depends on certain factors. What are that factors are? Directly proportional to area of cross section of the fluid, solid material. Larger the area, it's like a doorway for more heat to go. So directly depends on area of cross section. Also directly proportional to difference between the temperature of two ends. If theta 1 is greater than theta 2, heat flows from left to right. Heat always flows from higher temperature to lower temperature. So directly proportional to temperature difference theta 1 minus theta 2, assuming theta 1 is more than that of theta 2. Also directly proportional to time of flow. How much time you allow it to flow, more heat will go automatically. And finally, it is inversely proportional to length of the conductor. Larger the length, it takes more time or it is more difficult for the heat to go from one end to other end because it has to overcome each of the particles in the journey, each of the molecule in the journey. So these are the factors on which the heat flow depends on. Directly proportional to area, directly proportional to temperature difference, directly proportional to time of flow, and inversely proportional to length of the conductor, right? Combining both all of them will give you dq is directly proportional to area, temperature difference, time of flow, and inversely proportional to length. dq is the amount of the heat that flows from one place to another place. Now say for example you want to calculate the rate of flow of heat. Rate of flow of heat means dq by dt, that is how much of the heat flows per second. Just get this dt to the other side into the denominator. That becomes directly proportional to area. Theta 1 minus theta 2 is delta theta by L. That is dq by dt. To eliminate the proportionality, we can put a constant. That constant is called a proportionality constant. That constant is called coefficient of thermal conductivity. But I want you to be little careful that this is a proportionality constant. So that K is not going to depend on any of the equations that are mentioned there like area, delta theta, or L. No, it's not going to depend on any of them because you change area, dq by dt will vary, but not the value of the K. K rather depends on nature of that solid material. There are some materials who are conductive, who pass heat through them comfortably like iron. There are some other materials who don't pass heat through them like wood. So for the material who pass the heat, for whom pass heat, K value is high and vice versa. So K value is high and vice versa. So coefficient of thermal conductivity is a measure of flow of heat. More the value of the K, more the conductive nature, more the value of the K, and more heat passed through that. Right? Now, as we have written, the formula is rate of flow of heat dq by dt is K A delta theta by L. So I have to write the units of that K, SI unit of K, if I want to write coefficient of thermal conductivity. dq is heat, that is measured in joule, by dt is time, that is measured in second. K you have to find out. Area of cross section SI system is meter square. Delta theta is Kelvin or degree centigrade. By length is again meter. So 1 meter can be cancelled. Joule per second is rate of energy, that is also called watt in SI system. So watt equal to K, coefficient of thermal conductivity, meter, and then Kelvin. Be careful, this K is Kelvin, this K is coefficient of thermal conductivity. So the SI unit of coefficient of thermal conductivity K is watt per meter. This M comes to the denominator, per Kelvin, or watt meter inverse Kelvin inverse. That's the SI unit of coefficient of thermal conductivity, and it depends on nature of material but not on physical dimensions. You can also write further what is its dimensional formula is. Dimensional formula, if you are interested in writing, I will use the same. Just a second. I will use this formula to write a dimensional formula. dq is energy. Heat is a format of energy. Dimensional formula of energy is ml square T power minus 2 by dt is time. T equal to, for K you have to find out area L square. Delta theta can be represented like Kelvin, by length is L. So if you rearrange m L square T power minus 2, it goes to the numerator, it becomes minus 1, minus 3 equal to K, 1 L can be cancelled, and then Kelvin. Be careful, the last K is Kelvin. 1 L can be cancelled here also. So the dimensional formula of that K is m L T power minus 3 by Kelvin, or ml T power minus 3 Kelvin power minus 1. Like that we can find out the coefficient of thermal conductivity, units, and dimensional formula. I want you to tell you carefully that it depends on the nature of the material but not on physical dimensions. Be clear about that. That's what about coefficient of thermal conductivity, its SI units and dimensional formula. That's it. Thank you for watching.